Hi everyone, I'm Davey, and today we're going to be talking about the three methods to solve a quadratic, and we'll look at one example and see what each of the three methods gives. Two of the methods, one of the method always works, and the other two sometimes work and sometimes don't, depending on what the quadratic looks like. So we'll see that in action with this one. In this case, the one that always works will of course work. One of the ones that sometimes works will work, and the other one that sometimes works will not. So the quadratic that we have is x plus 3 squared equals 6. Now, why is this a quadratic? We call that a quadratic is an equation that we get by taking x, and x squared, and multiplying them by numbers and adding them together. Unfortunately, x plus 3 squared equals 6 doesn't look like that, but it is equivalent to that once we expand out x plus 3 squared. To see that, we can FOIL out x plus 3 squared, or use the trick for squaring a binomial, if you remember that, which is that a plus b squared equals a squared plus 2ab plus b squared. If we apply that to x plus 3 squared, then we get x squared plus, 2ab in this case is 2 times x times 3, which is 6x, plus then b squared is 9. However, we have a 6 on the other side. So when we then subtract 6 from both sides, we get 3 on the left side, 9 minus 6, and on the right side, 0. So this equation, x plus 3 squared equals 6, is equivalent to x squared plus 6x plus 3 equals 0. Is this a quadratic equation? Well, yes, because we have an x squared piece, an x piece, and a piece that's just a number, that is an x squared term, an x term, and a constant term, each of which might be multiplied by a number, and they're all added or subtracted together. Basically, we don't have anything that's a power higher than x squared occurring. We don't have anything like 1 over x, no square roots, or anything like no square roots or trig functions or anything like that, just x squared, x put together with numbers. Now, after some practice, you'll see something like x plus 3 squared equals 6 and immediately recognize that as a quadratic. But if you want to be sure there's something as a quadratic, you can always expand it out and see if you can put it in this form, where the general form of a quadratic formally is a times x squared plus b times x plus c equals 0. That's the general form of a quadratic equation. Any equation that can be re-expressed, that can be transformed into this form, is a quadratic. If it can be written as something times x squared, where the something is just a number, plus something times x plus something equals 0, then it's a quadratic. And in this case, the equation can be written like that. So that's what a quadratic equation is. Now, what are the methods for solving a quadratic equation? Well, the most basic method is the method that would let us solve an equation like x squared equals 2. So let's look at that method first. How would we solve the equation x squared equals 2? So again, we're going over the first method for solving a quadratic equation. Well, if we only know about fractions, then there's no way to solve it. There's no fraction that satisfies that. No fraction squared equals 2. That was something proved by Pythagoras or one of his disciples more than 500 years BC. But there is a notation that lets us express the answer to this. Nevertheless, it's something you probably won't prove into a real analysis course, that there is a square root of 2. But assuming that there is a square root of 2, the square root of 2 is, by definition, the solution to this. What I mean by that is that if we assume that there is some number whose square is 2, then we call that number the square root of 2, and the square root of 2 is then a notation for the solution to that equation. What we do in high school math then is we stipulate that every positive number, not negative numbers, but we stipulate that every positive number has a square root, and we write it like we use that notation to express it, and we then have a notation for the number that satisfies this. In other words, we assume that because 2 is positive, we assume that there's something that satisfies this equation, and we call it root 2. So by definition, by that assumption, root 2 is a solution to this equation. However, root 2 is not the only solution to this equation. Why? Well, the key reason is because a negative times a negative is also a positive. For example, what if we have the equation x squared equals 1? How do we solve that? Well, it might seem obvious the solution is just 1, right? 1 squared equals 1. We don't need to make an assumption to get a square root of 1. We already know that there is a square root of 1. 1 times 1 equals 1. But 1 isn't the only solution to that. Basic rules for multiplying negative numbers, namely that a negative times a negative is a positive, tell us that we also have that negative 1 times negative 1 equals 1. Indeed, that's the only way to make the rules of arithmetic work. So because 1 times 1 is 1 and negative 1 times negative 1 is also 1, we have that 1 and negative 1 are both solutions to this equation. Both of their squares are 1, whereas nothing squares to negative 1, because the square of a positive and the square of a negative are both going to be positive always. So we'd write the solution of this equation not as x equals 1 or as x equals negative 1, because neither of those is the complete solution, but we'd write x equals 1, comma, x equals negative 1 to show that both are solutions. Or, if we want to be compact about it, for some reason that's not rating. Okay, cool. If we want to be compact about it, we can write x equals this symbol, 1, where that symbol is read as plus or minus. X equals plus 1 or x equals minus 1. That's what that symbol means. It means the sign can be either positive or negative. So that's the simplest possible quadratic, essentially, I guess, except for x squared equals 0, which has its only solution, x equals 0. The simplest one besides that is x squared equals 1. And we see that that has two solutions, positive 1 and negative 1, so the nicest way to write the solution is x equals plus or minus 1. X squared equals 2 is similar. It has square root of 2 as a solution by assumption. You want to prove that the square root of 2 exists rigorously, take a row analysis course in college. It's still going to have two solutions once you assume square root of 2 exists. It has square root of 2 as a solution, and also the negative square root of 2 as a solution. So x equals plus or minus square root of 2 is the full solution to x squared equals 2. In general, if you have any quadratic equation of the form x squared equals c, the solution is going to look like this. X equals plus or minus the square root of c. If c is 0, x squared equals 0, then this gives you the single solution x equals 0, because positive 0 and negative 0 are both equal to 0. And 0 is, of course, the square root of 0, because 0 times 0 equals 0. If c is positive, then you're going to get two different solutions, the positive square root of c and the negative square root of c. If c is negative, though, then if you haven't learned about complex numbers yet, you should say there are no solutions, because there is no real number that is the square root of a negative number. 0 squares to 0, a positive number squares to a positive, and a negative number squares to a positive as well, because both positive times positive and negative times negative equal positive. So if you're trying to solve the quadratic x squared equals c, where c is negative, then the solution would have to be square roots, positive and negative, of c by definition of square roots. But there is no square root of c, we saw. There's nothing that we can square to get c if c is negative. Unless you've learned about complex numbers, in which case it's perfectly fine to talk about the square root of a negative number. It's just a complex number. And x equals plus or minus the square root of c is the right way to write the answer. Okay, so in general, x equals plus or minus the square root of c lets us find the solution to any quadratic in this form. So this method of solving a quadratic is called square rooting. It works whenever the quadratic is written as something squared equals a number. Whenever the quadratic looks like that, we can take the square root of both sides, except we have to remember to take both the positive and the negative square root, because they can both be solutions. If x squared equals c, then x could be the square root of c, or it could be negative the square root of c. Now, this quadratic that we have here, the example that we're using to illustrate these three methods, x plus 3 squared equals 6, well, it doesn't quite look like this form, because it's not just x squared equals c, it's something something squared equals c. But a key thing to remember in math, and this is very important, is that any rule you learn for manipulating expressions can still be applied if those expressions are not just variables, but more complicated expressions themselves. For example, this binomial squaring rule we reviewed over here, a plus b squared equals a squared plus 2ab plus b squared. That works for variables a and b. And of course, it works if we substitute in for a and b other variables, x and a, m and n, p and q, and so on. The precise variables don't matter. This is a purely algebraic rule that is true simply by virtue of how our standard operations of addition and multiplication work. But we can say even more. It's not only the case that this is true for all variables, but it's even true when we substitute expressions for a and b. For example, if we write x squared plus b and try to square that, well, that is actually equal to x squared squared plus 2 times x squared times b plus b squared. We could simplify that further by writing x squared squared as x to the 4th, but the point is that even though x squared is not just one variable, we can still apply this rule to it. An algebraic rule describes relationships between addition and multiplication, or subtraction and division, that hold for all numbers. The reason this rule is true is because whatever a is, and the reason the first rule is true, I mean a plus b squared is a squared plus 2ab plus b squared, the reason that rule is true is because whatever a and b are, whatever numbers they are, the way addition and multiplication work, namely in this case the commutative properties and the commutative properties of addition and multiplication, the way they work, and the associative property of addition, these properties tell us that whatever a and b are, whatever numbers they are, this is going to hold. If we sum them and square them, it's the same as squaring the first one, adding twice their product, and squaring the second one. And x squared is also a number, just like a. A plus b squared equals a squared plus 2ab plus b squared isn't really a property of variables, it's a property of numbers. It says for all numbers, a and b, this is true. In particular, if a is the number x squared, whatever x is, it's going to be true. For all numbers x squared, it's true, because x squared, if it's a number, is, in particular, can also be represented by a, because a can represent any number. We could do something even more complicated. We could write x plus y squared plus 3b. And then it would similarly be true that this is equal to the square of the first thing, x plus y squared x plus y to the 4th, plus twice the product of the two things, twice x plus y squared times 3b, and then plus the square of 3b. So no matter how complicated expressions are, we can always substitute them into an algebraic rule that's always true, called an identity. Any rule we learn, like the rule for the square of a binomial, if we plug in expressions for the variables, it's still going to be true. Because it's a rule not about how we manipulate variables, fundamentally. It's not about that. It's a rule about how addition and multiplication work. For all numbers a and b, it's saying these operations on a and b are the same. X plus whatever x and y are, whatever b is, x plus y squared is going to be some number, and 3b is going to be some number. So we can apply this rule that holds for all numbers to those two numbers in particular. Going back to our attempt to apply the square root method of solving a quadratic to the quadratic x plus 3 squared equals 6, we say, hey, the reason the square root method worked is because the square root is by definition an inverse function to x squared, which is a fancy way of saying that it undoes x squared. Saying x squared equals c is exactly the same as saying that x is the square root of c. That's what it means for x to be the square root of c. It means that when we square x, we get c. or x might be the negative square root of c. This thing with a plus or minus is a little technicality you have to be aware of, but otherwise, x being the square root of c means the same thing as saying x squared equals c. What is actually perfectly true is that x being plus or minus the square root of c means x squared equals c. So keep track of that plus or minus, otherwise square rooting is just the opposite of squaring. So we can apply that to x plus 3 squared equals 6. How do we do that? Well, x plus 3 squared equals 6, by the definition of the square root, is equivalent to, this notation means equivalent to, this double arrow, saying that x plus 3 is either the square root of 6 or negative the square root of 6. Right? Something squared is another something, if and only if the first thing is the square root of the other thing. Okay, x plus 3 squared is 6, if and only if x plus 3 is one of the square roots of 6, either the positive one or the negative one. The method of square roots is simply the method of exploiting that fact to rewrite the solution, to write the solution of the quadratic as square roots. And that works whenever we can write one side of the quadratic as a perfect square and the other side as a constant. I'll say that again. So the reason the method of square roots works here is because we can write this side as a square. It's something squared, something nice, not something with weird square root squared, but just a simple thing with x's and numbers squared, a simple linear function. And the right side is just a number, that is, a constant. Whenever we can write a quadratic like this as square equals constant, that's when we can apply the square root method. When it's square equals constant, we can square root the square to get the nice thing that's inside of it, and square root the constant. And then we have something similar. Now, this isn't quite a solution to the quadratic yet, right? We have x plus 3 equals plus or minus root 6. That doesn't tell us what x is. But what this is now is it is a linear equation, where a linear equation is an equation that involves x and involves numbers, but no x squared, no 1 over x, nothing like that. It just has x's multiplied by numbers and added to numbers. This is like a linear equation. This is something we know how to solve from pre-algebra. We solve it by subtracting 3 from both sides. X plus 3 is plus or minus root 6, if and only if x equals minus 3 plus or minus root 6. Now, the plus or minus makes things a little weird. There are really two equations we're trying to solve here, two linear equations. X plus 3 equals root 6, and x plus 3 equals minus root 6. For both of them, the solution is found by subtracting 3 from the right-hand side. Now, to be perfectly precise about it, we could write the equation separately and show that indeed, if you look at the two solutions, they are minus 3 plus root 6 and minus 3 minus root 6, or minus 3 plus or minus root 6. But as you get more familiar with plus or minuses, it'll become intuitive that in a situation like this, we don't really have to write two separate equations. We can keep the two equations together via the plus or minus sign and just subtract 3 from both sides. This makes sense because if x is either plus positive something, minus 3, or minus something, minus 3, then that's the same as saying it's plus or minus something, minus 3. That's basically what's going on here. Whether the sign on root 6 is positive or negative, we get that x is minus 3 plus that, plus root 6 with that sign. So that's why the solution to the linear equation is just given by x is minus 3 plus or minus root 6. And we got that linear equation, again, from taking the quadratic equation we started with and square rooting, which we could do only because it was written in a form where square rooting made it a nice linear equation. It was written as a square equals a constant. Whenever a quadratic equation looks like that, we can apply the square root method. Of course, there's a slightly more general case in which we can do that too. Maybe we have an equation that looks like this, x plus 1, or you know what, I'll start a new board. X plus 1 squared minus 4 equals 0. Well, okay, now the left side doesn't look like a square, right? The right side is just a number, 0. We can square root that, but the left side doesn't look like a square. So I guess we can't apply the square root method, right? Well, actually we can. We just need to rewrite this slightly. If we add 4 to both sides, then we get x plus 1 squared equals 4. And now we can apply the square root method, getting x plus 1 equals plus or minus the square root of 4, or plus or minus 2. Now x plus 1 equals plus or minus 2 is equivalent to x equals negative 1 plus or minus 2, which is either negative 1 plus 2, 1, or negative 1 minus 2, negative 3. In fact, any quadratic can actually be fiddled with enough to make it amenable to this square root method. This method works for any quadratic provided we fiddle with it enough, right? In the simplest case, it's just x squared equals c. We know how to apply the square root method to that. That's really easy. That's the definition of the square root. In a more complicated case, the quadratic is like some nice linear function squared equals constant, or some nice linear function squared plus a constant equals 0. And in that case, we also know how to eventually solve it with square roots. It turns out that we can get any quadratic into that form and then use this method to solve it with square roots. And if we do that and formalize everything with variables, what we're able to prove is a formula that does all this work of solving something with square roots. After getting it into the right form, it does all that for us, and all we have to do is plug it into the formula. And this thing works for any quadratic. That's the quadratic formula. So again, the way we get the quadratic formula is by taking a quadratic, a general quadratic. We don't know what the coefficients are. We say, okay, whatever the coefficients are, how would we solve it? And we say, well, we have to get it into this form where we can apply the square root method, right? We'd have to fiddle with it until it looks like something like this. You know, some square plus something else. And then once it looks like that, we can apply the square root method. If we do this in the most general possible setting, we say whatever the quadratic is, let's try to fiddle with this general quadratic where the coefficients are variables instead of numbers, right? So that we apply it to all quadratics at once. If we look at this general quadratic with variable coefficients and try to do the square root method on it, fiddling and fiddling until the square root method works, that's how we derive the quadratic formula. I won't present the derivation here, but I will present what the formula actually is. So we do this thing, we get square roots to work for any quadratic, then we get this quadratic formula, which tells you that if your quadratic that you want to solve looks like ax squared plus bx plus c equals 0. And if all quadratics can be made to look like that, right? The only issue is maybe you have some stuff on both sides of the equation, right? Or maybe it's not expanded out. But if you multiply all the factors out, and if you move everything to the left side of an equation, you can guarantee that your quadratic is in this form. And that's important for applying the quadratic formula. In order to apply the formula, you need to make sure your quadratic looks exactly like this. A represents the coefficient, that is the number that's multiplying x squared. B represents the number multiplying x, and c represents the constant, the number that's by itself. If there's stuff on the right side, if the right side equals 0, you can't apply the quadratic formula until you move that stuff to the left side. It has to be in this form. Just like you have to use the right language if you're trying to program a computer, you have to write things in exactly the way the computer knows how to analyze them. When you're using the quadratic formula, you have to plug the right things in for a, b, and c. If you have the quadratic in a different form, and you pretend that things are a, b, and c, when actually they're not the right a, b, and c, then you'll get the wrong answer. The formula only works if you put in the right input, if you tell it what it wants to know for each parameter, a, b, and c. So if I write a quadratic like 2x squared plus 3 minus x equals 0, for that quadratic, actually, a equals 2, b equals negative 1, and c equals 3. Even though I wrote 3 before minus x, b is still going to be the number multiplying x, which in this case is minus 1, because subtracting something is the same as multiplying it by minus 1. And c is the number that's by itself on the left side, which in this case is 3. So keep that in mind when using the quadratic formula. You have to be really careful what you substitute in. That is, what you take to be the value of these 3 parameters, a, b, and c, that are going to occur in the formula. The formula says find a, b, and c, then plug them into me, and I'll give you the 2 or 1 or 0 solutions to the quadratic. Okay, so what actually is the formula? if you write your quadratic in the form ax squared plus bx plus c equals 0, where a, b, and c are 3 numbers, and one assumption needs to be satisfied here. In order to apply the quadratic formula, we need to know that a is not 0. Yikes, what if a is 0? Then what do we do? Well, if a is 0, then there is no first term here. It's just bx plus c equals 0, and that's linear. We know how to solve linear equations. We have easy methods for that. That's pre-algebra. Ax squared plus bx plus c is the form of any quadratic that's non-trivial. That's not just linear. Trivial means it doesn't matter, right? If it's linear, it's easy to deal with. It's easy, simple, right? If it's not linear, if it's actually a legitimate quadratic, then a is not 0, and we can apply the quadratic formula. If you try to apply the quadratic formula when a is 0, you will divide by 0, which gives you nonsense as an answer. So don't do that, and only apply it when a is not 0, but if a is 0, then you're good anyway, because you can just solve it as a linear equation. Okay, so in our case, of course, we had a legitimate quadratic. This x plus 3 squared equals 6. This is a legitimate quadratic. A was 1 here, right? A is 1, B is 6, and C is 3. So it's a legitimate quadratic. We can apply the quadratic formula. The only question is, what is the quadratic formula? Well, the quadratic formula is as follows. If we have a quadratic, ax squared plus bx plus c equals 0, what are the solutions given by? Well, the solutions are negative b plus the square root of b squared minus 4 times a times c over 2 times a. Zoom in a little here and fix that. Okay, so these things we can all calculate using the coefficients, right? Except there's one extra addition. We have to put plus or minus there, because the square root can be either the positive or negative one. They're both going to work. Now, this looks sort of like what we got from the square root method, in that there's a plus or minus in that too. And the reason is, like I said, the way we prove this formula is we apply the square root method to the general case of a quadratic, to the quadratic whose coefficients are a, b, and c. Instead of specifying exactly what a, b, and c are, we say, okay, let's pretend we know what a, b, and c are, and let's do some manipulations with them. Let's do some manipulations that work no matter what they are. That is, let's do some algebra with them. And then get a formula that works so that for any a, b, and c, if we form the quadratic with them as the 3 coefficients, then this is going to be the answer. And we do that by manipulating it until we can apply the square root method, applying that, and then getting our solutions. So, okay, so this is the general formula. Remember the minus sign on b, remember to take plus or minus on the square root, and remember to keep the minus signs correct, minus 4ac. So if a is minus and c is positive, then this becomes a positive sign, right, on 4ac. So keep track of signs like that. And 2a in the denominator. Again, we don't have to worry about a being 0. That's only going to come up when it's not really a quadratic anyway. All right, so here's our quadratic formula. I didn't prove it, but let's apply that to our case and check that we get this to our given equation. And check that we get the same answer, in minus 3 plus or minus the square root of 6, that we did using the square root method. Okay, so our quadratic, written in the form ax squared plus bx plus c equals 0, is x squared plus 6x plus 3 equals 0. So a is 1, b is 6, c is 3, like we said. Okay, so write that down. A is 1, b is 6, c is 3. What does that give us? Well, negative b is negative 6 plus or minus root b squared is 36 minus, well, 4 times a times c is 4 times 1 times 3, which is 12. So minus 12 over 2 times a is 2. So that's negative 3, breaking up the fraction, plus or minus root 24. I'll say 1/2 root 24. Okay, so this doesn't quite look the same, right? Before we had minus 3 plus or minus root 6. Now we have minus 3 plus or minus 1/2 root 24. But the key thing here is to remember that we have some rules for simplifying square roots. They are what we have to use here. So the first rule, the main rule we have for simplifying square roots is this. And that's the rule we're going to need to use here. The square root of a product of two numbers is the product of their square roots. Now, this does not hold when we replace multiplication by addition. The square root of the sum of two numbers is not the sum of their square roots, but for multiplication and division, this is true. Why is it true? Well, it essentially comes from the fact that square roots are defined based on multiplication. The square root of a number is that number which, when multiplied by itself, yields the original number. Because of this definition, it's pretty easy to verify directly from the definition that square roots multiply this. I'll leave that as an exercise. But assuming they do, there's a nice way to simplify things, like the square root of 24. What we can do is write out 24 as a multiplication as thoroughly as we can. What does that mean? Well, what it means is we take the prime factorization of 24. We break it up into as many factors as we can, and then see whether breaking the square root into a product of square roots will turn out to be helpful. So what is the prime factorization of 24? Well, it's 3 times 8. 8 is 2 cubed. So it's 2 cubed, 2 times 2 times 2, times 3. Now, we can get then that the square root of 24 is equal to the square root of 2 times the square root of 2 times the square root of 2 times the square root of 3. Okay, the square root of 2 times the square root of 2 times the square root of 2 times the square root of 3. All right. Now what can we do here? Is there anything nice we can say about that? It seems like we've just made it more complicated, right? We started with one square root, the square root of 24, and now we've got a product of 4 square roots. But notice that we can use the definitions of the square roots actually to simplify this a bit. The point of the square root of 2, its defining property, is that its square is equal to 2. But look here, we have the square root of 2 squared as part of this product. We have the square root of 2 times the square root of 2. We can replace that quantity then by 2. That's the defining property of the square root of 2, that we multiply it by itself and we get 2. So this is equal to 2 times the square root of 2 times the square root of 3. Can we simplify this more? Well, unfortunately not. 2 and 3 don't have anything in common. They're both different prime numbers. But we can put the square roots back together, reversing this rule to get the square root of 6. 2 square root of 6. There are other ways to do this manipulation that might be more intuitive for you, but the basic idea is that 24 is divisible by a perfect square, namely 4. And when we broke it up like this, the square root of 4, which is 2, popped out. Because in this formula, square root of a times b, if a is a perfect square, then the square root of a is just going to be a regular number instead of another square root. So instead of turning one square root into 2 square roots, if we apply this formula where a is a perfect square, then we started with the square root of b, that's a square root, ended up with the square root of a, which is just a number, because we're assuming a is a perfect square, times square root of b, which is a square root again. So if we assume that a is just is a perfect square, then we end up with just a number times the square root of something smaller. So in a sense, then, we've simplified the square root. We can do that precisely when the original number under the square root has a square, perfect square as a factor. Then we can break it up as a product with that perfect square. So because 24 is divisible by 4, because it had 2 occurring twice in it, right? Because the prime 2 is repeated, then we were able to pull out this factor of 2, and then what we're left with 6 has 1 factor of 2 and 1 factor of 3, so no more squares we can do anything with. But this is the basic idea for how we simplify square roots. We look for factors we can pull out by breaking the square root up across the factors, and then we want to put the factors back together again to just get regular numbers, so that we end up with a smaller square root out of what's left. So in this way, square root of 24 gives us 2 square root of 6. How does that help us then? Well, we had negative 3 plus or minus 1/2 square root of 24 before. We just said that square root of 24 is equal to 2 square root of 6. So let's plug that in here and see what we get. Well, if we write 2 square root of 6 instead of square root of 24, what do we get? Well, negative 3 plus or minus 1/2 times 2 square root of 6. Well, the 2 in the numerator and denominator cancel. So what we get is plus or minus square root of 6, which is what we got before. Yes, over here. So the two different methods for this quadratic are for the same solution, the square root method, which works for only some quadratics or all, depending on how far you're going to go, or in which case it's called completing the square. Or the quadratic formula method, which definitely works for all quadratics. It's based on formally completing the square and applying the square root method. So applying both those methods to our example quadratic, where the square root method just involves writing it in a form, we can take the square root of both sides, adding a plus or minus sign, and the quadratic formula involves writing it in a form where we can find a, b, and c, then applying the formula, plugging everything in, and if necessary, simplifying square roots, using this idea of pulling out factors that are the same and finding copies of regular numbers built out up of the square roots by their definition. Using that simplification, we should end up with the same answer by either method. Now, I'll say a brief bit about the third method that doesn't actually apply here, which is factoring. I'm going to assume you're familiar with factoring here, but I'll just review a little bit about how it works and why it doesn't work for this particular quadratic. So factoring applies to a quadratic, which again, the general form of a quadratic is ax squared plus bx plus c equals 0. And factoring is a way of looking at the quadratic and realizing that we can write the left-hand side as a product of two things. Now, there's no general formula for factoring a quadratic that's at all nice. I want to stress that. You can't, there's a quadratic formula for finding the solutions, and that does give a formula for factoring it, but it looks gross and has square roots in it. Not all quadratics can be factored in any nice way. That is, not all quadratics can be factored using only integers, but some can. And the way to deal with that is really on a case-by-case basis. There are heuristics and tools to learn, but if you can't figure out how to factor a quadratic, the solution is always just to try the quadratic formula. So factoring a quadratic is the method of looking at the quadratic and trying to rewrite it as a product of two factors which are both nice and simple. They're both just linear. They both just have x and no x squared in them. For example, let's say we have a quadratic, x squared plus 5x plus 6 equals 0. Well, can we write the left side as a product of two nice things? Well, if we wanted to get x squared, it seems like we probably need x and x. So they should be terms in each of the two factors. We should have an x in both factors so that we get x squared and multiply them together. And then what? Well, if we have plus something and plus something, if we FOIL it out, and this is the general rule that you should remember with factoring, these two somethings here should add to 5, but multiply to 6. They have to multiply to 6 because their product gives the constant term, and they have to add to 5 because multiplying one by x and multiplying the other by x gives you the two middle terms. So what two numbers add to 5 and multiply to 6? Well, 2 and 3. So x plus 2 and x plus 3 are the two factors. Multiplying them out, we get x squared plus 2x plus 3x, which is plus 5x plus 6. So this is a way to factor this quadratic. X plus 2 times x plus 3 equals 0. The solutions are then the solutions to each factor because, and this is the key property, a product is 0 when its factors are 0. Its product is 0 if one of its factors is 0, and otherwise it's not. That's the only way a product can be 0, if one of its factors is 0. That's known as the zero product property. So using that, we say, okay, what are the solutions to this? Well, we could have x plus 2 equals 0, which is the case when x equals -2, or x plus 3 equals 0, which is the case when x equals -3. This is a really nice method to solve quadratics, but it doesn't always work. Sometimes we'll try to factor and we'll get stuck. In particular, note that this method can only give one kind of answer. It can only give you integers or fractions. If you had something in front of the x squared here, you could get fractions. But this method is never going to give you solutions that aren't integers or fractions, because once you factor into integers and fractions, I'm assuming, each of these factors has only integers and fractions in it, and you're not going to get square roots anymore because you lose the square, right? the only way you can get something that's not an integer or fraction as a solution to a quadratic equation is by square rooting. And if you solve by factoring, you're losing the square. So by the time you actually solve linear equations, there aren't any more square roots. There's no way that you're going to square root in this process, right? You factor, no square rooting happening there because we're just factoring into integers, right? That's what I'm assuming. I'm saying factoring into integers cannot give you irrational solutions. It can't give you solutions that aren't fractions. If you factor into integers, you still have integers here. And then when you solve equations with integers, you can only get fractions as the answers. Never square roots, never anything irrational. So isn't that a contradiction though? Because we looked at this quadratic, the example one, x plus 3 squared equals 6, and we saw that the answer does have a square root in it. It is in fact irrational. How is it that this quadratic has irrational solutions, which we're able to verify both from the square root method and from the quadratic formula? And yet I just said that when we factor a quadratic, we can see that the solutions are always going to be rational. Well, the answer is that some quadratics don't factor. Some quadratics cannot be factored with rationals, with fractions and integers. Indeed, if we look at our quadratic here, which was x plus 3 squared equals 6, or expanded out, x squared plus 6x plus 3 equals 0. X squared plus 6x plus 3 equals 0. If we try to factor that, we say, well, like before, we want an x in both terms, and then we have two somethings here, two numbers, which should add to 3, which should multiply to 3 and add to 6. Are there any two numbers that multiply to 3 but add to 6? 3 times 1? No, they add to 4. So no, there is no way to factor this. This quadratic doesn't factor. It's irreducible. You can't factor it into smaller integer pieces. It doesn't factor. You could factor it if you let square roots be in the factor, but that's not at all helpful, right? You don't want to do that. That's messy and gross. You can't factor this, right? So if a quadratic can be factored, what we've shown is if you can factor a quadratic, you get solutions that are just integers or fractions. If you can't factor it, then maybe you get solutions that aren't integers or fractions. In fact, it's an if and only if. Well, no, because maybe one solution is irrational, one is rational, but basically you don't have to worry about irrational solutions if it factors. So we have this thing that we proved, right? We proved if it factors, and write this out here. If it factors, then we know that the solutions are rational, are fractions. So I'll say if it factors, then it only has rational solutions. Only rational solutions if it factors. So that means something else. Whenever we have an implication like this, whenever we prove that something means something else, we've proved more than just that one thing. We've also proved something called the contrapositive. If I tell you that all men are mortal, a classic example in logic, then you know that if I give you a man, you can say, oh, okay, that's a man, that's mortal, right? But you can also tell me something else. Well, if I give you something that's mortal, it doesn't mean it's a man, right? It's true that all men are mortal. No man's live forever. No man's going to live forever. But not all mortal things are men, right? A turtle is also mortal, even though they live for quite some time, and a turtle is not a man, right? So man implies moral. Moral doesn't imply, man implies mortal. Mortal doesn't imply man. And also, mortal doesn't imply man. But not mortal does imply something. If I give you something and say, hey, this thing isn't mortal, then you can say, oh, well, that thing better not be a man, right? Otherwise, you would have showed me an immortal man. There are no immortal men, right? If you know that all men are mortal, you also know that all immortal things are not men. They can't be, or else you'd have an immortal man, which is precisely the thing, the non-existence of which the statement, all men are mortal, asserts. That's called the contrapositive. In general, if you know P implies Q, you also know that not Q implies not P. If P were to give you Q, and we have not Q, then we can say, oh, P better be wrong then, because P would contradict what we know. Right? That's a basic principle in logic, which maybe sounds complicated, but hopefully isn't as complicated in actual practice. In this case, We know that if a quadratic factors, it has rational solutions. So what this principle tells us, this contrapositive principle, is that if a quadratic does not have rational solutions, that is, if it doesn't have rational solutions, if there's an irrational solution, then it doesn't factor. Because if we have a quadratic that didn't have a rational solution that somehow factored, well, that would be a contradiction. Because we know if it factors, it has a rational solution. So no rational solution means it doesn't factor. Applying that to our case, we say, well, our quadratic, x plus b squared equals 6, we already showed it doesn't have a rational solution, therefore it doesn't factor. Which makes sense. Indeed, that's what we found, that it doesn't factor. So without even checking whether it factored, we could have already known that it wasn't going to factor. Because if it had factored, then we would have had to get rational solutions, but it doesn't have any rational solutions. So those are the three methods for solving quadratics. Factoring sometimes works if the quadratic is nice, but many times it doesn't work. So the way to solve a quadratic is to first try factoring it for a little while. If that works out, great. You can just look at the individual linear factors and solve them like linear equations because you know that the left-hand side is going to be 0 precisely when one of the factors is 0. Okay, so you could do it by factoring, but if factoring doesn't work, then maybe there are rational solutions and you just didn't see the way for factoring to work, right? Maybe you will end up with rational solutions and factoring did work, you just didn't see it, okay. Or maybe factoring genuinely does not work objectively because there are irrational solutions. So when factoring doesn't seem to work, whether or not it actually works, what you should do is try the quadratic formula, or if you see a way to do it, try applying the square root method directly. If there's any way to get the quadratic in the form, you can take the square root of both sides and get something simpler, then do that. Those are the three methods. In general, the square root method in factoring might just not work, so then you'll have to resort to the quadratic formula, which is a matter of getting the quadratic in the right form, so you know all the coefficients, plugging them all in, and simplifying any square roots you might get in the answer. So this is how you handle solving quadratics. These are your three methods. Of course, to explain how to factor, I need to say more, but factoring is not essential. It's a really good tool to have, but any quadratic that can be solved by factoring can also be solved by the quadratic formula because the quadratic formula covers everything. The only exception is if the a coefficient is 0, but then it's not really a quadratic, it's actually a linear equation. So that is how one can solve quadratics.